My pleasure to, well, welcome our own Alex Krolewski, who is visiting us from Waterloo, apparently. Um, so Alex did his PhD at University of Berkeley with Simone Ferrara and with Martin White, and we established that he would be my academic nephew if people do keep track of that sort of thing. Um, so he worked on larger scale structure, one of my favorite topics. After finishing his PhD, Alex started a postdoc here as this is your sorry, this is your first year here, right?
Yeah, first
Yes,
year.
your first year. So just I guess, yeah, 6 months. He's been here for 6 months now. He has the prestigious AMTD Fellow, which is a new fellowship, which is established at the University of Waterloo. Um, he's, of course, a postdoc at the Waterloo Center for Astrophysics, and he was also an associate postdoc. Actually, no, he's a part-time postdoc at Parameter Institute. And he's going to tell us about cosmology from CMB lensing tomography at Redshift 2. Thank you.
Okay, great. Thanks for the introduction, Niyash. So yes, yep. So I will be talking about how we can use CME lensing tomography to learn about large-scale structure out to Redshift 2 using galaxies from the unWISE catalog. And so I just wanted to start by thanking my co-authors. So a lot of this work was done during my PhD at Berkeley. So I just like to thank Simone, Martin, and Eddie Schlafly. Okay, so yeah, so I'm going to start off with an introduction to where we are in cosmology today and introduce you to the lensing S8 tension as a sort of interesting topic to be followed up on, and then I'll talk about how we are trying to use CMB lensing cross correlations to learn about whether this tension is coming from new physics or potentially from systematics and either weak in the measurements that are going into that tension. And so to do that, I'm going to motivate CMB lensing and describe how we can how we've made the highest signals noise measurement of CMB lensing cross correlations to date, and one that will allow us to get percent level constraints on the matter power spectrum, and therefore actually weigh in on this S8 tension. So I'll be talking, so I'll motivate our cross correlation measurement. I'll present the measurement. I'll talk a little bit about some systematics. I will talk about how we're planning to do cosmological parameter inference. Unfortunately, I'm only going to be talking about sort of our method and tests on simulations today. The results on data are not quite ready, but I think already with the tests on simulations, we can see that we're going to have a pretty interesting and competitive measurement. And then at the end, I'll talk about some future work and some other work that has come out of our analysis of these unWISE galaxies. Right, okay, so I just wanted to start off with a few-minute overview of where we're at in cosmology and sort of what is this business with this discrepancy between Planck and weak lensing surveys, and why do we think we can address it with CMB lensing cross correlations. So I'm sure everybody here has seen this famous pie chart that's showing that we have a very well-established model of the universe that says that 95% of it is not ordinary matter. And this measurement is really sort of best established by our measurements of the cosmic microwave background. That is using photons that were emitted by the photon-electron fluid in the early universe when the universe was ionized before it transitioned to being neutral. And so that emission from the cosmic microwave background you're seeing on the top of the slide. And the sort of key thing about the CMB that makes it so interesting and constraining for cosmology is all the structure we see. And that is coming from the fact that in this photon baryon fluid, you have gravity and pressure acting as opposing forces, setting up these acoustic oscillations, which leads to a pattern of hot and cold spots that you can see in the map, right? You can see these sort of characteristically sized spots in the map. Or if you take its Fourier transform down in the bottom and map out temperature fluctuations as a function of angular scale, you can see all this rich structure in the Fourier transform. Basically these spots in the map are translating into the peaks in its Fourier transform. And the key thing here to notice is that the blue line is a model fit and the red points are the data. And so really this model is doing spectacularly well at reproducing the data. And so this is really why we think this pie chart on the left is so well supported by data. It's because of this comparison. And so for another look at this, these plots are just showing how our knowledge of the parameters of this model have advanced over the past 20 years from pre-WMAP, that's around sort of where we were around 2000 to today in 2018. And you could just see the error bars and all the parameters shrink basically to the size of the dots. That's very impressive. So basically now we're in this situation where we have a well-established standard model for cosmology. And of course, if you look at the matter parameter on the right, so this, you have to divide by 2 powers of the Hubble constant, but you still get something that's like 30% of the critical density of the universe. So basically we're in a universe where most of the components of the universe are, most of the universe is not either baryons or dark matter. Okay, so where does that leave us? So the CMB has given us this super precise measurement of super precise constraints on a lambda CDM model. So is that all? Like, should we just pack up and go home? Is there any reason to do anything else? And it turns out that, in fact, there is more to be learned beyond just what we can get from Planck. And there are a couple reasons why, and in particular, an interesting place to look is the large-scale structure of the universe, where we're probing the distribution of galaxies and matter in the sort of lower than redshift 1100 universe. The universe much closer to us than the surface of last scattering. And there are a few reasons why this is interesting. So first, the CMB is super powerful, has a lot of rich physics, but it's still only a single measurement coming from this surface of last scattering, the time when the universe transitioned from ionized to neutral. And so you can think of it basically as constraining the cosmological model at that time and providing a prediction for the distribution of the universe as we see it today. So if we go out and measure the distribution of matter in galaxies, we can test that prediction. And of course, in this way, large-scale structure is really also probing the time evolution of the universe, basically how those structures are building up, and it can also probe extensions to the lambda CDM model. And it is also particularly sensitive to dark energy, which was basically a negligible component of the universe at redshift 1100, but today is about 70% of the universe's energy density. And the second reason why we're interested in using large-scale structure in addition to the cosmic microwave background is that large-scale structure probes much more volume, and in theory, there's much more information than what we can get out of those CMB fluctuations. And already with Planck, we're beginning to saturate the information that we can get from CMB. So Planck is sort of the best that we can do on CMB temperature. We can still measure CMB polarization better, but we're kind of getting to the end of all of the information we can get out of the CMB. And so now we're kind of moving to a future where our best cosmological constraints are going to come from the large-scale structure. But for the moment, we're really more in this first regime where we can think of large-scale structure as providing a test of the lambda CDM model as sort of constrained by Planck and giving a prediction for how the universe should look. So how do we do this? Well, we can't directly predict the distribution of matter in galaxies in the universe, right? Because whether or not there's a galaxy at a given position is kind of random. This depends on basically random features of the initial conditions. You know, was there an upward fluctuation that leads to a galaxy or a downward fluctuation that leads to a void? But that fluctuation in the initial conditions is basically random. So instead, what we need to do is we need to look at the statistics of the density field and compare that to our models for the density field statistics. And to do that, we take advantage of the fact that the density field is Gaussian on large scales. And so this means that all of the information in a Gaussian field can be encapsulated in the power spectrum. That is the fluctuations as a function of scale. So this power spectrum that I'm showing here is similar to the power spectrum of the CMB fluctuations that I was showing, except here we're thinking about fluctuations in the matter field rather than in the CMB temperature field. And I should add that in the matter distribution case, the approximation, the field is not purely Gaussian. There is a lot of information beyond just the power spectrum. But in this talk, I'm only going to be talking about the power spectrum information, which is kind of our primary way of extracting information from the density field on large scales. And so here I'm going to talk about basically the constraints that we can get from the gross shape of this power spectrum. So you can see that it goes up, and then it starts to decline on smaller scales. And so this means, you know, the sort of key parameter sensitivity that I'm going to be talking about from this shape comes from these two parameters: omega matter, that is the matter density of the universe, which governs the shape of the power spectrum, and sigma 8, which is the amplitude of the power spectrum, which is basically telling you how clumpy or smooth the universe is. That governs its amplitude. And so here, you know, I'm showing the dependence on sigma 8, and so really you scale sigma 8 up. That really is, it's just defined as a scaling of the amplitude of the power spectrum. The scaling with omega matter is a little bit different. So that's actually changing this turnover scale. And so the reasons for this come from the way that this power spectrum is actually generated by the growth of perturbations in the universe. What happens here is inflation initially lays down a power law initial power spectrum that looks like the rising part of the power spectrum on the left of the plot. And so this is, you know, this power law power spectrum kind of on all scales. And in particular, you know, the power spectrum is, you know, extending on all scales. And even though at early times, the horizon size is quite small, you know, that is a region of the universe is only causally connected to sort of very nearby regions. So in the early universe, because radiation redshifts faster than matter, that early universe is radiation dominated rather than matter dominated. And this means when you have a perturbation try to collapse, its collapse is opposed by radiation pressure that sets up those acoustic oscillations that we saw in the CMB. And so this means that fluctuations that are within your very small horizon, they're going to try to collapse, but they'll be opposed by radiation pressure. And so that means that basically fluctuations that are inside the horizon scale cannot grow. They are suppressed. And this will continue to happen until the universe becomes dominated by matter rather than radiation, at which point there's no radiation pressure and the fluctuations can grow. And so what's going to happen as the universe evolves is that this horizon scale on which the perturbations are suppressed gets bigger and bigger and bigger and bigger. That is, it's moving from right to left on this plot as, you know, size increases to the left. And eventually at a certain point, you get to a point where the universe becomes dominated by matter, perturbations can grow, And so that means that the small scale perturbations have been suppressed, but the large scale perturbations have not been. And the scale of this is set by the matter density of the universe. And so that is why this power spectrum is sensitive both to the amplitude and to the matter density, which is setting this turnover scale. Okay, so that's great. So we have our measurements of the power spectrum. And so we can go out and actually measure the power spectrum from weak lensing surveys. And actually what we're doing here is we're not just measuring the power spectrum, but we're measuring some projection of the power spectrum across a non-zero distance. And so this basically is why we're only sensitive, if we go back here, we're only sensitive to the gross shape and not to these wiggles, which are going to get washed out as we project over sort of the power spectrum from different redshifts. And so with measurements of the universe from weak lensing, we can measure the combination of these parameters, sigma 8 and omega matter. And since these measurements basically probe a narrow range in scales, we can basically only measure a degenerate combination of the two parameters, which is often defined as this S8 parameter. But the interesting thing is if we look at this plot on the bottom left, you can see the lensing constraints are the sort of larger contours along this degeneracy direction. And you can see that they're a little bit off from the gray Planck contour. And so this is about a 10% tension in this S8 parameter that's basically along this degeneracy direction. And so that's, kind of intriguing, right? It's like a 2 to 3 sigma tension here. You can also see this on the plot at the bottom right that's showing S8 for these different lensing surveys. This has also been borne out by analyses of the redshift space power spectrum of galaxies here in the top, where again, omega matter and sigma 8 are coming in a little bit low compared to what we'd expect from the CMB. And so then, of course, this raises the question, this is not a super significant tension, so it's not like extremely worrying yet, but what exactly is happening here? Is there some new kind of physics? Is the growth rate a little bit different from what we thought? Or is there some systematic in the measurement? I think people are usually quick to accuse the weak lensing measurements, but I think it's also possible that there could be something going on with the CMB measurement as well. So we'd like to try to address this question with CMB lensing. And so what we want to do is we want to come up with a similar measurement of the amplitude of structure, but one that has very different systematics profiles, and then see if we get the same answer or not, and then we can see whether systematics and weak lensing measurements are the culprit for this tension. And so what we do is, rather than measuring the weak lensing of galaxies, we actually measure lensing of the cosmic microwave background. And so for galaxy lensing, what you're doing is you're taking a whole bunch of very faint source galaxies, and you're looking at correlations in the ellipticities of those galaxies induced by the stretching of the light from the galaxies as it propagates to us. For CMB lensing, you do something very similar, but your source, instead of being these faint galaxies, is the cosmic microwave background itself. And this actually leads to a characteristic imprint in the CMB that's quite different from the primary CMB. And so on the right, that's what this figure is showing. You have the CMB temperature in a simulation in the left-hand panel. And then the center shows the change in the CMB from lensing. And you can see that this is really quite a different, quite a distinct shape from the primary CMB. And so in a more technical sense, what we say is happening is the primary CMB is very Gaussian, and the change in the CMB from lensing is very non-Gaussian. And even though that change is quite small, the fact that it has this very distinctive shape means that we can extract lensing. And then you can make basically a reconstructed map of the mass density of the universe out to the CMB over on the right. Okay, so that's fantastic. So just like with weak lensing, with CMB lensing, we can map out the projected mass density of the universe. However, there is a big disadvantage to CMB lensing, and that is that we only get a single source plane coming from the CMB emitted at redshift 1100. So it's very powerful because it's sensitive to even matter at high redshifts, but in galaxy weak lensing, if you wanted to look at matter at different redshifts, you would simply look at source galaxies that are closer or further from you. For the CMB, we can't do that. So if we want to get sort of tomographic information about the matter density, we're going to need something a little bit different. And in fact, we can do that by cross-correlating the CMB lensing signal that we extract from our CMB lensing maps with galaxy samples. And what this will do is this will actually pick out the contributions to CMB lensing from large-scale structure associated with those galaxies. And so that's what this sort of cartoon is showing. If you have galaxy samples that are at different distances from us, the cross-correlation of those galaxy samples and the cosmic microwave background lensing is going to probe basically how the large-scale structure at those redshifts is deflecting the cosmic microwave background. And that will show you, and that basically allows you to map out the amplitude of structure as a function of redshift for these different galaxy samples. And so this actually allows you to get tomographic information about the matter distribution rather than just a single integral all the way out to the surface of last scattering. Now, while we need the galaxies to get tomographic information on the matter distribution, adding galaxies to the mix is going to introduce additional complications. And that is because galaxies are biased tracers of matter. Their clustering is enhanced relative to matter. And so this is coming from the fact that galaxies don't just form everywhere in the matter field, but they really only form at the very highest peaks of the matter field. And so this schematic is kind of showing what happens. So if you have the underlying wiggly line is kind of your matter density field, and then galaxies only form at the very highest peaks. So you can see that the galaxies are much more clustered than the matter density. And this fact that the galaxies are only inhabiting the highest peaks means that their clustering is biased by a constant multiplicative offset from the matter clustering. And the amplitude of that offset depends sensitively on exactly how high are the peaks in which the galaxies form, which basically comes down to a bunch of very complicated physics about what was happening when galaxies were forming in the very, very early universe, which is not really something that we can measure right now. And it's something where it's hard to have a sort of theoretical expectation for how this should work. So essentially what this means is that the amplitude of the power spectrum is arbitrary because it depends on this arbitrary galaxy bias. So that's a little bit unfortunate because now you've destroyed your sensitivity to the amplitude of the power spectrum. So to get back that sensitivity, we must also add the galaxy autocorrelation. So we're basically considering two power spectra, the cross correlation between CMB lensing and galaxies and the autocorrelation of the galaxy field. And this is because the cross correlation is going to have one power of bias, since we have one power of the galaxy field, whereas the autocorrelation with two powers of the galaxy field will have two powers of the bias. So the combination of the two, if we combine them in the right way, we can cancel out the bias dependence, and we're just left with the dependence on the amplitude of the matter field. And here also in this equation, I have switched from power spectra P of K to CL. So P of K is the power spectrum in physical units, and CL is the projection of the power spectrum onto the sky, where now it's an angular power spectrum measured as a function of the angular wave number L. And so this is actually what we're going to measure. We're not actually measuring, we're actually measuring some basically integral over the power spectrum across the range of redshifts probed by our galaxy sample. The other important consequence of this fact that we need both cross-correlation and autocorrelation is that it tells us what signal-to-noise we need on our cross-correlation detection to get a given signal-to-noise on the amplitude of the power spectrum. And so this comes from the fact that when we're measuring CME lensing cross-correlations, we basically have the galaxy field, which is quite well measured, and the CMB lensing field, which has a relatively high noise due to the reconstruction that we've had to apply to extract it from the primary CMB. And so that means that the error on the numerator CL kappa G is much larger than the error on the denominator CLGG. So basically the signal to noise of the amplitude of the power spectrum is going to be equal to the signal to noise of the galaxy CMB lensing autocorrelation. So that basically tells us what signal to noise we need to target if we want to measure the amplitude to sort of a few % precision to weigh in on this 10% discrepancy. We're going to need sort of like a 50 sigma measurement of the kappa G cross correlation. And so here I'm showing a number of sort of previous measurements of this cross correlation. And you can see, people have gotten 10, 20, even 30 sigma measurements, which is good, but you're still only getting kind of to the, you're not really getting to the point where you can definitively say something about this lensing tension. You really want to get an even higher significance measurement than what has been done in the past. So how do we do that? How do we build the best possible CMB lensing large-scale structure cross-correlation? So what are the ingredients here? So first of all, how are you going to get your galaxy sample? You could go out and get a galaxy sample that has spectra for every single one of your galaxies. And then you have a very nice, well-characterized galaxy sample. Unfortunately, galaxy spectra are very expensive. And in this measurement, we have a projected CMB lensing field that's really a 2D map of the projected mass density. And that's what we're going to cross-correlate with the galaxy field. And so that means that we really don't need redshift information for each and every one of our galaxies in our sample, because in the end, we're really only going to consider the projected galaxy distribution anyways. So we don't need a redshift for every galaxy. We just need an understanding of the statistical redshift distribution of the galaxies. So that basically tells us that it would be a lot better to use imaging surveys rather than spectroscopic surveys because they're much cheaper, they get us more galaxies, and we can still statistically characterize their redshift distribution even without having a redshift measured for each galaxy. And the other key that we have is that we want to use an imaging survey, and it also helps if you can use an infrared imaging survey. And this is because galaxies are actually, old stellar populations are actually brighter in the infrared than in the optical. And then additionally, as you redshift them to higher redshifts, they become even brighter in these infrared bands. And so that's what this picture is showing, where I'm showing redshift 1 galaxy in Sloan imaging on the left, and then in WISE imaging on the right. This is at 3.4 and 4.6 microns. And, this is 3.4 microns in the picture. And you can see that this galaxy is much, much brighter in the infrared imaging. And so this means that, even though the WISE satellite is a much smaller telescope than Sloan, it's only a 0.4 meter telescope, it can actually get, since it's looking for galaxies that are brighter, it can actually pick out a larger sample of galaxies. In particular, it can pick out a larger sample of galaxies too high redshift, where we're taking advantage of the fact that the largest contributions to the CMB lensing kernel are basically coming from distances halfway between us and the CMB at redshift 2. So the closer to redshift 2 you can push, the better. The other advantage for WISE for this work is that it's an all-sky satellite mission, unlike optical galaxy surveys where you can only get, you're in one hemisphere, so you can only get, part of the other hemisphere's sky. And this is advantageous because the best CMB lensing maps that we have also come from an all-sky survey. So if you have, galaxies from the entire sky, you can exploit that synergy and get higher signal to noise. So the sample that we're using is coming from basically a reprocessing of the WISE infrared data that has about 5 times as much, 5 times as long exposure times as the official WISE release. So that's shown here. The pictures down at the bottom comparing the 1-year WISE data to the 5-year unWISE data that we're using. And so this leads to a catalog of about 2 billion galaxies that's publicly available at this URL. And then these are the papers describing the catalog. But basically, this is the best infrared, all-sky infrared data set that we have. And it's among the largest galaxy catalogs that are available today. We sort of have, I think, more galaxies overall than, for instance, DES. Great, so we have this huge sample covering the whole sky. We measured the sky in 2 infrared bands. Can we actually select galaxies? And it turns out that we can select galaxies at different redshifts, even only from these 2 infrared samples. This plot on the left here, what we've done is we've taken our unWISE galaxies and we've matched them to deep photometric redshifts in the cosmos field. And then we're showing that different color cuts on these 2 WISE magnitudes can pick out galaxies at different redshifts. And we've basically created 3 different galaxy samples going from low to high redshift. And the table is giving the sort of rough parameters in terms of mean redshift and number density of these samples. The other key thing is making sure that our sample is free of stellar contamination. And so again, you just have these 2 WISE colors that's not really going to be that good at separating stars from galaxies. And even more damning is the fact that we go back here. Sorry, if we go back, oops. Here you can see that WISE really has a poor angular resolution. So to WISE, really everything is going to look like a point source, regardless of whether it's a galaxy or a star. However, what we can do instead is, it turns out we can actually subtract, or we can actually remove most of the stars from our sample using photometry from the Gaia satellite. So basically take each WISE source, ask if Gaia thinks it's a star, and if so, exclude it from our sample. And it turns out that the depths of these 2 surveys are actually quite well matched, such that this eliminates basically all of the stellar contamination in the sample. And when we compare to the deep imaging in Cosmos, where with the Cosmos imaging, you can actually separate stars from galaxies, we find that the residual stellar contamination is only about 1%. So this actually does a really good job of removing most stars from the sample. You might be wondering what exactly these galaxies are. So here I'm kind of showing basically a plot of 4,000 angstrom break strength against O2 equivalent width for the unWISE galaxies in basically the blue and the green samples. The red sample we didn't have quite enough archival spectra to make these plots. But you can see basically that these galaxies are a mixture of star-forming quiescent galaxies, and then you have some AGN sneaking into the higher redshift samples. And so on the bottom, I've just shown some representative spectra. You can see some of them have 4,000 angstrom break. You can see emission lines, and you could see some quasars in these samples. Okay, great. So we've defined the samples. We can cut out contaminated regions around stars, around large galaxies, around WISE imaging defects. And when we plot the distribution of these unWISE galaxies, things look pretty uniform. So that's, indicating that there are no sort of large systematics affecting the sky distribution of these galaxies. So I'll just flip through the sky distribution of the samples. You can see things look pretty uniform. So we have our projected galaxy map, and then we take our CMB lensing map that we get from Plock, that is basically extracted from the non-Gaussian impact of CMB lensing on the CMB temperature and polarization. And then what we do is we just Fourier transform and cross-correlate the two samples. And so, as I said before, we need both the autocorrelation and the galaxy CMB lensing cross-correlation to constrain cosmology. And so, so here I'm showing those detections. And in red, I'm just showing a theory curve at fixed cosmology where we just allowed the biases to vary between the auto and cross correlations, and the detection significances are on the top.
Hey, Alex, can I ask? So for comparison, you also have this red curve that says theory, no shot noise.
Mm-hmm.
So does that mean that the blue points have been shot noise subtracted?
Yes. That's just so that I could get all three of them on the sort of same plot scale. The red is much lower number density, so it would have much higher power spectrum if I left the shot noise in.
Right. So for the shot noise correction, do you assume that it's just 1 over n?
No, we let the shot noise be a free parameter.
Oh, okay, great. Okay, cool, thanks.
Mm-hmm. And we're also including magnification bias in this red theory curve. So the combined significance of the three samples is about 80 sigma. And so that's, the highest sort of other detection is about 30 sigma. So this is quite a bit higher. So that's fantastic. Okay, of course, if you have very high statistical significance, you need to be even more careful about systematics, really making sure that you're not systematics limited. So now I'm going to talk a little bit about some of the systematics in the measurement and in the modeling. So the sort of largest systematic is measuring the redshift distribution of these galaxies. So as I said before, we don't need a redshift of each one of the galaxies for the cross correlation. We just need the redshift distribution. But then the question is, how do we do that? So this is a catalog of galaxies with just 2 infrared fluxes. So photometric redshifts are completely impossible. Basically the 3 samples kind of exhaust the photometric redshift information that we get. We can just, so that's not, right. So as an alternative, we can actually measure the redshift distribution from cross correlations with spectroscopic galaxies with very well-determined redshifts. And so this technique takes advantage of the fact that galaxies are clustered. So if you go out and you see sort of an overdensity of galaxies on the sky, that likely means that the galaxies are physically associated, at least on a statistical level. You can have chance correlations between galaxies, but sort of statistically, the fact that you see correlations between galaxies on the sky indicates that they must be correlated in 3 dimensions. And so just as an example here I'm showing just a slice of the sky, and pretend that you only had a spectrum, an exact redshift from this one galaxy at redshift 0.1. However, you saw that there was this huge overdensity of nearby galaxies. So from that overdensity, you could infer that a lot of these galaxies are likely lie at the same redshift as this redshift 0.1 galaxy. And in this example, we of course have more spectra, and so we can check and we can see that yes, in fact, these galaxies nearby are at the same redshift. So this is sort of how things look on an object by object basis. Of course, it's very noisy. Some of these galaxies are not going to be associated with this one galaxy that we had spectra for. So really what this is a statistical statement where you take all of your galaxies with unknown redshift distribution and you cross-correlate them with galaxies with known redshift distribution in a narrow redshift slice. And then the more correlated that these two samples are means the higher the fraction of the unknown galaxies that lie at the same redshift as this narrow redshift slice that you have. And so we can turn this back into sort of more familiar language by saying we measure the cross correlation between our unknown sample and our known sample in narrow slices, and that cross correlation is going to be proportional to the redshift distribution of galaxies. It will also be proportionate to the bias evolution of your unknown sample. And for what we're doing with CMB lensing, this is actually a good thing because, if you remember, when we cross-correlate galaxies with CMB lensing, we have a power of bias as well. And of course, that bias can evolve in redshift. So if your sort of measurement of the redshift distribution also includes the bias distribution, that kind of takes care of modeling that part of what you need for the galaxy kernel. And so the way that we do this is we basically take all of the large galaxy samples from SDSS with well-known redshifts. And so this plot is showing in black, I'm showing the spectroscopic samples in some narrow redshift bins. And basically going from galaxies to quasars, so we can span the entire range of the redshift distributions of the unWISE galaxies. So we take that cross correlation, we subtract off contributions from magnification bias, we divide out the known bias evolution of the spectroscopic samples, then we combine these four different, the measurements from the four different spectroscopic samples, and then that gives us this measurement of bias evolution times redshift distribution here for our three different galaxy samples. And so then we can use this measurement of redshift distribution in our modeling. And so then the question is, oh, sorry, let me go back here. So this redshift distribution is coming from cross correlations with some error bars on them. And so those are the basically the red points with error bars. And this leads to some uncertainty in the redshift distributions where I've drawn, and we can basically draw samples from the redshift distributions that make up these gray lines. And so the question is, how does that uncertainty propagate to our modeling of the cross correlations with lensing and the galaxy autocorrelation? And so what I did here is I took so I basically took the data, or I divided by the, I said, what if we model the data not using our best fit redshift distribution, but rather using these different samples? How much would that change our model? And how does that compare to the error bars on the data? And here, basically, this is showing that the impact of this uncertainty in the gray bands for the autocorrelation is quite similar to the statistical error on the cross correlation in the blue bands, which is the dominant source of statistical error. So this is basically telling us that the uncertainty in the redshift distribution is going to have a sort of similar contribution to the overall uncertainty in our measurement. Okay, and then switching gears a little bit, another sort of test of our measurement and of our redshift modeling is to look at the cross spectra, between the different galaxy samples. And so here, basically, I'm comparing those to the data, and this is more sensitive to the redshift distribution. So those samples are again shown in gray. But you could see that basically the data, or the model is doing a pretty good job of reproducing the data given these redshift distributions. That provides kind of further validation of our approach. And then finally, this is just a massive plot showing a whole bunch of different systematics tests that we did, both in terms of how we're measuring the cross-correlation redshifts, or in terms of sort of details of how we're measuring the galaxy CMB lens and cross-correlation in terms of stellar masking, things like this. And so basically what we want to make sure is that the uncertainty or the changes of these various different systematics is no larger than the statistical uncertainty in the measurement. And basically we can see that that's true both for the cross-correlation here, and then for the autocorrelation, where we're going to be dominated by redshift uncertainty, we basically verify that that is the dominant systematic and everything else is quite a bit smaller. So now I'm just going to talk a little bit about how we're working on cosmology constraints from this sample. And here I have to apologize for being a bit of a tease. I'm only going to be able to talk about cosmology constraints from, or what we're doing on mocks right now, because unfortunately our constraints on data are not quite ready to show, but that hopefully should be coming out soon.
So what if we promise not to tell anyone? Would that be? That's okay.
Yeah, sorry. Right, okay, so basically the idea here is we have some mock sample and we want to test our cosmology pipeline. And basically we demand that we can reproduce the cosmology of the mocks within half sigma shift for the parameters on noiseless simulations. And so here I'm showing basically we can do this for this green sample. We're still working on the other two samples, so that's why I'm not showing the results on data quite yet. But for green, at least, things seem to be looking pretty good. And yeah, so here again, I'm showing a number of different tests that we did. For tests on noiseless mocks, we demand less than a half sigma shift in the cosmology from truth. We also did a test on noisy mocks to verify that our model has, chi-squared approximately degrees of freedom. Basically the model is a good fit to the data. And in the mocks, we're getting about 2 to 3% errors in omega matter and sigma 8. So that's kind of telling us about how well we think we can do in data. And again, like I said, these are tests for the green sample, which seem to be passing. We're still working on the other two samples before we can unblind and look at the cosmology constraints from the data. Another sort of interesting side note here is that we've done some testing of different models. So our fiducial model is linear bias times halo fit. Basically linear bias times sort of a fitting function for the nonlinear matter power spectrum. And so we also tried, instead of using this fitting function for the matter power spectrum, a perturbation theory based approach where you, which is a little bit more principled, where you have all the biases allowed by symmetries and a bias expansion. And unfortunately, this model was a little bit harder to work with than halo fit. And so we wound up basically just restricting our analyses to the scales in which halo fit would work well. But we had some difficulties with this model in terms of sort of prior volume effects on the sort of large number of unconstrained bias parameters that we have to marginalize over. And we also, it also seemed like this model was giving a slightly worse fit to the data than halo fit. And we think this may be because of the large range of redshifts in the data, means that you're always going to have some sensitivity to very low redshifts where the perturbation theory fails rather dramatically. So I think the question of how we can do the modeling on this data is still, it's still an open question of how to best do the modeling here. And what we're basically focused on is coming up with a model and a scale cut that can work, but we're hopeful that maybe with further work we can improve some of these issues and hopefully model to smaller scales. And then the final point that I wanted to show on our cosmology constraints is what we're doing about the uncertain redshift. And so here what we do is we took our model and we said, what if instead of using the true DNDZ that we know in the simulation, we used samples drawn from the DNDZ with the same error distribution as in the data? How would that change our results? And then, so that's this plot on the left where I'm just showing omega matter and sigma 8. And you can see that there's some shifting of the contours. And so then what we did is we just averaged over these samples, weighted by the Bayesian evidence of the best fit, which for all practical purposes basically is equivalent to weighting them equally. Basically all of these different DNDZ models are just as good a fit to the data as the truth. And so this basically broadens out your parameters a little bit. And it looks like it's leading to about a 10% increase in sigma 8 and omega matter. So as I said, these are the tests that we've done on the green sample where things seem to be looking pretty good. And we're still working on the other 2 samples before we apply to data, but we're hoping to have this result out relatively soon. And so now in the last few minutes here, I just wanted to talk about some related work and some future steps. So the sort of first thing that I wanted to talk about is improving the redshift distribution measurement that we have. And so as I said, the redshift distribution here is our largest source of systematic error. But we can do better. And so while we don't need a redshift for every single galaxy in the sample, if we can get redshifts for a representative fraction, we can actually measure the redshift distribution to better precision than what we have. And so the dark energy spectroscopic instrument is just coming online in April, and it can measure spectra for 5,000 galaxies at once. So this is a sort of great application for us. And we're actually very fortunate that they have, in addition to the main cosmology program, there's a secondary program for observations of other targets. And so with just 3 DESI pointings, a little bit less than 5 hours of observation, we can obtain 15,000 redshifts, which would be enough to reduce the uncertainty from the redshift distribution that we have right now. And so that's very exciting. That's kind of ongoing work, and we hope that that will sort of help validate our existing work. And then there are just a couple other different cross correlations that we can do with the unWISE galaxies that I wanted to talk about. The first is the integrated Sachs-Wolf effect. And so this is coming from the red shifting and blue shifting of photons as they move in and out of potential wells. Basically photons are propagating from the CMB going through potential wells, red shifting and blue shifting. If the potentials are constant, there's no net effect. But if the potentials are decaying, then there would be a net blue shift. And it turns out that in the late time universe, because of dark energy, gravitational potentials are decaying. And this induces a correlation between CMB temperatures and galaxies. And so this cross-correlation called the integrated Sachs-Wolf effect is actually direct evidence for dark energy as seen through the decay of these potentials. So we can make this measurement cross-correlating unWISE galaxies with CMB temperatures. And this leads to about a 4 sigma detection of the integrated Sachs-Wolf effect. And so here I'm just showing the, we take some template for the ISW effect, scale it by this parameter AISW, and I'm just showing that for the 3 different galaxy samples. And then the final bit of work I wanted to show is I wanted to talk about a projected field kinetic SZ measurement with unWISE galaxies that was actually just out on arXiv a few weeks ago. And so here what we're doing is we're basically measuring the changes in the CMB temperature from as CMB photons scatter off electrons in, or sort of electrons in ionized parts of the universe or in galaxy groups and clusters. And so this inverse Compton scattering can either come from thermal velocities of the gas, or it can come from the bulk velocities of the gas. And so here we're actually thinking about the kinetic effect, where the velocity is that bulk velocity, which leads to no temperature distortions of the CMB, but it does induce correlations between temperature and velocity field. And so you can detect this KSE effect using projection fields only. And so this recent paper, which was led by Ola Kusiak and Colin Hill, makes this detection using galaxies from unWISE. And so I just wanted to briefly advertise this because I think it's a very, very nice paper. Ola did very good work. And it's an interesting paper in that we found an anomalously high amplitude of the KSE signal for the green and red samples here. And so this is just showing the measurement. You can see this amplitude of.
Can I ask you something? So if you square the temperature, all sorts of noise also would kind of leak in. For example, if there is, I don't like radio sources or dusty galaxies and things like that. So if they're not completely clean, if you square them, they're going to still be there and they're going to be correlated with the density field. So, I mean, how do you know that's not that?
Yeah, so really, Ola did a whole bunch of null tests for dust because, yeah, I mean, I think that is a big concern. We're basically looking at, so we took CMB temperature map that was already cleaned, then we cleaned it from dust further, and then we observed no cross correlation with dust templates. We looked at cross correlations between dust templates in the galaxy field and kind of tried to scale that down. So basically we did a large number of null tests to sort of prove to ourselves that this really does not seem to be dust foreground. And we checked with a number of different CMB temperature, CMB maps.
What about dust in the galaxies themselves?
So again, dust in the galaxies themselves would show up in these null tests, right? So
I think actually that's the primary dust that has been talking. I mean, that is the dust we worry about, right? Because
okay, he said foregrounds, which is what was confusing me.
Yes. Yeah, sorry, I guess by foregrounds here, I mean foregrounds to the CMB, which would include dust in the galaxies.
Mm-hmm. Right. Yeah, I mean, the main thing is, I guess, at high, I mean, we know at high frequencies, dust emission dominates over CMB and KSC, of course. And of course, you like to clean that, but that never works out perfectly. And this dust, I mean, large L's, it would be dust in basically redshift 2 galaxies, presumably. That's yeah. But yeah, so I guess you're saying that you check for it and if you think it's thoroughly cleaned.
Yeah, that's right. So it's a bit of a mystery.
Mm-hmm. Thank you.
Yeah, so one sort of thing that we've been exploring is the possibility that the theory model is breaking down at small scales, where effects from the unknown HOD are important. So plot on the right is showing the one halo contribution to the KSE squared across galaxy field. And it's showing at least that this one halo term is uncertain. I don't know that we're like definitely convinced that this is what's going on, but it's sort of just kind of an interesting detection here.
Mhm.
So anyway, so that's kind of all I have. So I'm happy to take more questions.
Oh, wonderful. Thank you very much. And almost on time. Let's thanks, Alex. Any more questions? I see Alexa's raised her hand. Alexa, you want to unmute?
Yeah, thanks. So the whole point of the CMB lensing is to get different sets of systematics than when you get from galaxy lensing, is what you said. And my understanding of the systematics with just regular galaxy weak lensing is that it has a lot to do with things we still don't know just about galaxies and baryon physics, like galaxy assembly bias and so on. So can you just talk a little bit more about how you're not introducing those same systematics back in when you do this kind of cross correlation with galaxy samples?
Yes. So you're definitely right that there is, both of them are going to have galaxy formation physics uncertainties, basically coming in through the bias model that we're using. So the advantage of the CMB lensing cross correlation here is that they generally probe larger scales, where we think that these effects are a little bit better understood. Like a lot of like assembly bias is a fairly small scale effect. And on large scales, galaxy bias really starts to behave like a constant, and so it's easier to treat. So that's an advantage of CMB lensing cross correlation. Intrinsic alignments are something that's only happen in the weak lensing case and not in the CMB lensing case. So again, that's a sort of systematic that CMB lensing doesn't have to deal with.
All right, thanks.
Thanks, Alexa. Shahab, go ahead.
Sure. I mean, we can definitely postpone this if we're out of time. But otherwise, I was going to ask, in terms of getting the cosmology constraints that you're showing us, so I guess there are two ways one can go about this. I guess you could either do in order to get the redshift distributions, you're doing the cross correlation, I guess you said with BOSS. So are you doing that and then feeding that bias times n of z factor into the cross correlation analysis with the CMB lensing, or are you folding all of these 2-point functions into a single self-consistent analysis? Are you doing the cross correlation with the CMB lensing and then the cross correlation with BOSS, and then I guess the BOSS auto clustering, and then you have the WISE or unWISE auto clustering as well. So I guess you technically could have 4 2-point functions in a self-consistent analysis. Or are you doing what I said initially, where you're just folding in that bias times n of z factor into the?
Yeah, so we're doing the former. So I think it would be a little bit more principled to do, as you're proposing, folding all of the 2-point functions into a single analysis. On the other hand, if we do things this way, it sort of more easily allows for different, basically the whole bunch of systematics that come into the, we kind of want to separate out the systematics from the redshift distribution from the cross correlation with CMB lensing and the galaxy autocorrelation. And so, the way that we're doing it kind of allows us to separate out those steps. We have some redshift distribution. We can sort of validate its consistency with redshift distributions that we get from photoz's and our expectation for sort of rough, reasonable expectations for how the unWISE galaxy bias might evolve. So yeah, so it's basically a little bit easier to separate out these different systematic effects, but I agree it would be a little bit more principled to model all the 2-point functions together.
And for the BOSS galaxy bias, are you just taking the measurement of that as an external prior?
So we're actually measuring the autocorrelation with boss galaxies in the redshift bins that we use.
Okay.
Yeah.
So that is okay. That is done in a self-consistent way, I guess.
Yes, that's right.
And then I had another quick question. You were mentioning that the maximum L value that should go to is 600. And I guess you're talking also about the perturbation theory modeling. So I guess for the redshift ranges that you're considering, do you have a sense for what K values you're peaking around in terms of the information content?
Yeah, so so for the green sample, which is at about redshift 1, if you just are considering modes at redshift 1, that L of 600 corresponds to K of about 0.3. However, the redshift distributions are very broad, so it's not entirely correct to think that way. And I think that this is part of the problem that we're seeing with perturbation theory models, is that you're still going to have non-negligible contributions from higher Ks where the perturbation theory might be breaking down.
Okay. Yeah, because I guess already at like L of 100 or so, you're starting to become, I guess for weak lensing alone, galaxy weak lensing alone, at around L of 100, you start to become sensitive to nonlinearities. But I guess that's something you can keep testing, or you can just test for it to see whether your results become more stable with more severe cuts, I guess.
Yeah, exactly.
Thanks.
The good thing.
Sorry, one more question if I can. Sorry.
That's okay, go ahead.
I guess you talked about your work in the context of the sigma 8 or SA tension. But given the redshift ranges you're probing, I guess for me, it seems maybe an equally or maybe even more important question is the constraint you can potentially put on the dark energy in that redshift range, which where it's fairly unconstrained at the moment. Do you have any thoughts on that?
So you mean like from the growth of structure from redshift 1.5 or something?
Well, so you're sensitive both to the growth of structure and the expansion history and the expansion rate between, I guess, from redshift 0.5 to 1.5 or so. Is that right?
Yeah.
And I mean, I guess at least beyond redshift 1, my understanding is we don't have any strong, I mean, at least the constraints there are not as strong as compared to the redshifts closer to 0.
Right. I think that's definitely something that we could try to measure, like fitting something like W0 and WA instead of constant dark energy. So yes, I mean, right now we're focusing on the 6-parameter lambda CDM fits, but yes, that's something else that we consider doing.
Thanks.
And on that note, I think we are, it's getting a bit late. If there's no more pressing questions, of course, Alex is not going anywhere. Neither of us are, actually, none of us are going anywhere. He's going to be available just one Zoom call away or one Microsoft Office away. And actually, there's going to be